All right. Hello, everyone. Yeah, sorry. You notice the contrast is not great. So this gives you a little history lesson on this room. And you notice that the floor here has this big circle. That's because way back when there used to be a bunch of blackboards here. And so the interesting thing about that is what could actually happen way back, even before I was here, is this whole thing used to be able to rotate. This whole floor used to be able to rotate. There'd be a bunch of blackboard stuff on here, and then they could have the demo equipment back there, and then they could hit a thing, and the whole section here would rotate. Obviously, that is no longer the case because you can see here it's a solid wall wherever that seam would be. Anyway, why do I mention that? The room now back there is actually the projector. So if I put my hand over this, you notice that it doesn't block any of the light. That's because the projector is behind here, and through the courtesy of looking through that window, the lights are on in that room. That's it. The lights are on in the back room, so I called someone and maybe they'll come and turn off the lights back there. I can turn off these lights as well. That's very likely why more lights were off. It doesn't really change too much, unfortunately, because, so it's just one of those. There's light, then there's more light, so you lose some contrast. So hopefully someone will come on by. I am actually going to send a quick message to someone and see if they'd be able to assist, and then I'll get started on things. There's someone in the building. Yeah, I don't know if those, I'll hit the light switch real quick. This is the aisle light, so, yeah. All right, so whatever, we'll make do. It's not the worst thing in the world. Everything still works. It's just lower contrast. All right, so reminder to you all, make sure you're looking through the problem sets. Make sure you're looking through the problem sets. If you have not even opened that document, that's not ideal. So reminder to you all, we have the quizzes each week. Those 5 questions are not, I can't cover everything I've taught you in 5 questions. It's just not possible. So make sure you look at the problem set and at least look through the problems and say, do I know how to do this? And if you're uncertain, you should probably try that problem. That's the trick to that. You need to, the reason the problem sets exist, and if you're like, where do I even find the problem sets? You can see all my back-end windows. I was trying to make labs. Where do I even find those? Web courses in the Files tab. Everything's there. That's where the PowerPoints are. That's where the problem sets are. It's where the formula sheet is, the current formula sheet that's going to be used for the exam. Everything is in the Files tab because I like it, because it's organized. It's like a file browser. It is a file browser. So boom, there's problem sets. You open it up and wow, there's the problems. If you have not looked at these, I highly, highly, highly encourage you to, because again, those quiz problems there's a reason each week has many problems on it, because there's many different types and all that jazz. What I cover in class, the quizzes, is not enough for the vast majority of people. So please look through these. The longer you wait, the bigger your backlog's going to be, and it will be rough if you start looking at these a week before the exam and you realize you don't know it. Don't end up in that situation. Yeah. How long is the exam going to be? So I guess there's 2 answers there. One is it's during a normal class time, so temporally it's going to be an hour and 15 minutes. Content-wise, currently what I'm leaning towards, I haven't started making the test yet. I'll start doing that in the next week or so. I am thinking about something like 15 multiple choice. And then there will be 3 free response questions that you'll pick 2 of, is the goal. Those free response questions will have 2 parts, a part A and a part B. Part A and part B will be independent of each other, meaning if you miss part A, you're not going to use the answer in part A and part B. That's because it's a 9-letter grade. And that's never fun, that when one problem relies on another, and you miss the first one, then you miss the second one. So keep that in mind. There'll be 2 parts, all that jazz. time-wise, here's the mindset. If I have like 15 questions, ideally, I make each question doable within 3 minutes. That's kind of like the max time you should need for any problem. And that's like more than you should need. 3 minutes for multiple choice, that comes out to 45 minutes, and then that gives 15 minutes for each free response that you choose to do. That's kind of the mindset here. So you get about 7.5 minutes for each part. Great. Generally, any test I make, I try to make it so I can complete that test in about 20 minutes. And that's not me like being brutal to you. That's me saying I obviously am making the test, so I know exactly what to do. So basically that 20 minutes is the time it would take if you knew exactly what to do to solve every problem. And that includes me actually writing out what I need to write out. That includes like writing time and everything. So if you knew exactly what to do, take you about 20 minutes to kind of write out everything and do it all. You have an hour 15. Again, that's kind of one of the ways I try to determine timing. Obviously, not all of you are going to know exactly what to do on every single problem because you're in the process of learning and all that stuff. So, all right. With that in mind, here is the plan for the next couple weeks. Yeah.
So on the first class, is there partial?
There is partial credit. Let me see if I uploaded the rubric for it yet. If not, I need to. Is it on this? No. All right. Sometime today or tomorrow, I'm going to show you all the rubric for it. It's a very, so that'll show, I'll put that on that formula sheet document. In fact, I'll show you it now. Let's see. It's one I've been using for a lot of my classes, so I can just pick any class and steal it. So this is the formula sheet from a previous class, but it's going to have the rubric on it. I'll post the rubric for you all. So this rubric will get posted. So each part of the question will be worth 10 points, and the rubric is set up such that I'm giving points to the things that determine whether you're doing the right process. So if you remember at the beginning of the class, there is a process to solve these problems, and I need to change the wording slightly here. First 3 points are, did you draw a picture well, and did you identify what you're solving for? Remember, that's the first step of any problem. Did you draw a picture well? Not every problem has a picture, but if you realize at this point, a lot of them do. Especially in this class. So picture, and then when you're solving for step 4, did you identify what you're, again, I'm switching things down slightly, so what I'm saying is not quite matching this. Picture what you're solving for, then another point, did you identify your givens correctly? Then 5, then the next couple of points are, did you identify the correct equations to use? And then did you use them appropriately? 8, 9 points, next kind of 1 or 2 points is just, did you do the math? Did you do the process correct? And then the last point is, did you get the right answer? So all that to say, if your entire process is correct and you make a silly mistake, you're just going to lose 1 point out of 10 on that. That's the beauty of partial credit. If it's a more significant mistake, maybe accidentally you put r instead of r squared and you consistently did that, like you wrote the equation as r instead of r squared, maybe it was 2 points out of 10, and then, more severe mistakes lose 1 point out of 10. Rubric works pretty well. Oh, and something I haven't mentioned to you all, maybe I did this at the beginning, I'm not 100% sure. If you do the math for the class, 50% of the grade is points that you should basically get. It's effort points. The quizzes, the recitation assignments, the recitation attendance, the clicker points, all of those kind of wrapped together equal 50%. You should get all of those points. If you get all of those effort points, the remaining 50% is exams. And if you do the math, if you get 50% of the effort points on the exams, you only need to average a 60 or above to get a B in the class. That's how the math works out. And 80% or above on the exams represents an A. Why? You are not going to get an 80% or above on these exams unless you know what you're doing. You're going to make a small mistake here or there, things like that. That's going to happen. Same thing even with the 60% or above. You will not get that if you don't know what you're doing. If you do not know what you are doing, you will get a bad, we're talking 30, 40%. You all have probably seen this in your calculus classes, and some of your maybe, if you started to get your engineering classes. The way these classes work is it's not based on how much knowledge you know, it's about whether you know the process. And it very much, if you don't know the process, your grade is just, it's bad. You all see grade distributions on STEM exams, and they're lower. Because we're not evaluating how much knowledge do you know. I'm evaluating, can you do the process? And that process, there's mistakes you might make that are a little silly, so you might do some mistakes. But that's why these and this is going to be true of all your future classes. It will not be uncommon for the exam average to be a 60, maybe even 50. So you will see it if you haven't already. And so I will be pretty happy if our exam average is in the 60s, because that means people are understanding what I consider to be a B in the class, on average. As rough as that sounds, it doesn't mean the exam is super brutal. Again, you all have hopefully taken a few classes now where you've seen this to be the case. If not, you will. It's going to happen. It's how STEM majors work. They're just built different. All right. Any more questions on this? All right. Yeah. Surface area. I do not plan. No, the formula sheet I have posted. Actually, let me. I can show you all the formula sheet that's currently posted, and that's the one that you all are going to have access to. It's over here in the Files tab. If you look at the formula sheet, it does not have the surface area, as far as I'm aware. Nope. But you all get a 5x8 note card. So if you think that's something that you need on it, put that on your note card. I put all the physics equations here. If there's things outside of physics you think you might need to know, surface area of a sphere, surface area of a cylinder, all that kind of jazz, feel free to add that. Yeah. Sometime next week I'll start bringing in note cards. Yeah. Next week I'll start bringing them into class. Grab one. Don't grab more than one because there's 300 students. If every student grabs one, it's 300 note cards. If every student grabs two, that's 600 note cards. I'm not bringing 600 note cards to class. That's a lot. Also, I have another class of 100 students. So anyhow, just keep that in mind. Once you grab a note card from me, don't lose it. I'm happy to provide them as long as I don't have to provide 1,000 note cards every test. Depends how quick. What's the question? This one?
Yeah. How come for U2 you're not counting U3?
Yeah, so this is a good recap. So last class we talked about electrical potential energy. This class we're going to talk about electric potential. The goal is that we'll start capacitors on Thursday. That'll roll into Tuesday. And then Thursday of next week, at least I'll cover resistors. I may or may not get to current. We'll see. Timing-wise, if not, that'll just be on the next test instead. So, electric potential energy, we had to build the system. So in this question, we had to build the system. So we first said, what's the energy required to bring one charge in? There was no energy required to bring one charge in. Now, what's the energy required to bring a second charge in? That second charge only sees the first charge.
Why?
The third one's not there yet. We build one at a time. Yeah, so that's the answer to that. We build one at a time. And as time goes on, they steadily see each additional charge. And the logic here and then the example I gave you all is this is why your all's phones charge so slowly when they get to 100%. Because every new charge you add has to see all the others before it. Yeah.
Why is U1 before 0?
Because there's no energy, there's no work required to move a charge where there's nothing else around it. It's not having to fight anything. What force is required to bring a charge where there's nothing around it? There's no force, there's nothing around, nothing I'm fighting against. To place that charge there, it's free. Because there's nothing else I have to fight against. Once I bring another charge, then I'm fighting. All right, so keeping things moving. I didn't do this one, so I'll quickly run through this one with you all. An electron is released from rest a distance z above a positively charged infinite plane with charge density sigma. What is the speed of the electron just before it hits the surface? Use Q, E for the charge of the electron, and ME for the mass of the electron. So this problem is just like dropping a water balloon, as weird as that sounds. One of the first questions on here was, hey, you drop a water balloon, how fast is it going? This is the same problem, as weird as that sounds, just the force is different. The force causing it, instead of it being gravity, now we have an electric force. So how do we solve this? We draw a picture for, what are we solving for? Solving for the velocity of the electron right before it hits. So if we draw a pretty picture of this, we got our infinite plane. It is useful. Like I've told you, I'll draw pictures. You're going to get good at drawing infinite plane or like a plane and stuff like that if you haven't already. It's a useful skill. Spheres, things like that. So we're going to put a charge up here. This is going to be my electron. And basically the question is, hey, it's above this positively charged plate. How fast is it going once it gets down here near the bottom? Velocity equals question mark, and then that's QE for an electron. So, how do we solve this? We're going to use conservation of energy. Now, something that's going to make things a little, different here. We're going to need to we're going to use conservation of energy. Why? Because this problem is just like a ball falling. Something starts with a certain amount of energy, it ends with then the energy changes to velocity. Rule of thumb, if I give you a problem on this test and I say how fast is something going, and this is test 1, you're going to use conservation of energy. That's a good rule of thumb to have somewhere in your mind. If I ask you a problem on test 1 about how fast something's going, that's a flag that it's going to be conservation of energy. So, to that end, we want to know how fast it's going. And so one of the rules is that the negative change in potential energy equals a change in kinetic energy. You're like, whoa, where did that come from? If I just write this differently, you'll see potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. These two things are identical. I'm just going to move stuff around and you're going to see that. Move the kinetic energy to this side, move the final potential energy to the other side. And so we get potential energy initial minus potential energy final equals kinetic energy final minus kinetic energy initial. All I did was move things around. Oh, the right side is the change in kinetic energy. The left side is the negative change in potential energy. And I'm going to put E because this is due to electric fields. If you're like, why is the left side negative? Because it's initial minus final. That's backwards. The right side is final minus initial. That's the definition of change. The left side is initial minus final. That's the negative of change. They're backwards. Great. So now we can say, how do I find the negative change in potential energy? And we go back and we look at there's an equation for this. That's in our previous slides. In fact, we could even let's see if it's on the formula sheet. That'd be nice, right? Oh, it's not quite on here. Maybe I'll add it. It's kind of here, but not really. It's here in a different form. Ta-da! Yeah, it's that one. Delta U, my change in potential energy is negative Q times the integral from I initial to final. The electric field dot the distance I travel. You're like, oh my gosh. It's not too bad. Negative Q times the integral of E dot ds. Oh, look, my negatives cancel. That's kind of nice. But funny enough, we're then going to see another negative pop up, so it's fine.
Where did the interval come from?
The definition.
Is this because it's only one charge?
It's because it's only one charge that's in an external field. What's causing that external field? The infinite plane below it.
Why isn't the negative on the floor?
The negative's canceled.
No, on the slide.
This one? Or this
Why
one?
is it positive on the left and negative on the right?
Just how the definite, it's the same thing. It ends up being the same, works out here. All right, so now we just need to set up this integral. This Q is going to be the charge of an electron. This E, the question is, what field is this charge in? What's causing so we got our charge, it's in a field due to some other charges. What is that field due to? The infinite plane. What is the equation for the electric field due to an infinite plane? Sigma over 2 epsilon naught. Where did I get that from? We derived it in a previous class. It's a Gauss's law problem. Feel free to check out a previous PowerPoint to see where that came from. I didn't pull it out of thin air. We did derive it. The electric field due to an infinite plane is sigma over 2 epsilon naught. If you're like, where did that come from? It's one of the problems in the problem set, and it's one we derived last class. So check that out. Now, Here's the thing we also have, there's a couple things we got to keep in mind here that are very important. What's the direction of this electric field? There's a dot product here. This is a vector, meaning we need to recognize the direction of it. In fact, I'm going to actually write, before I even put this electric field in here, I'm going to remind you all that this can be written as the magnitude of E times the magnitude of the path times cosine of the angle between them. That's a dot product. What's the direction of the electric field above a positively charged infinite plane? Is it up, down, left, right, or somewhere else? The electric field will point up. That's important. We're doing a dot product. We also need to know the direction it's moving. Which way will this negative charge move? It's going to move down. Why is all of that important? What's the angle between these? 180. We need to keep that in mind, and it's all going to work out, trust me. We're going to end up spinning out another negative that's then going to cancel with another negative. Trust the process. Trust the process. This angle is 180. I have not put the bounds of my integral yet either. Let's go ahead and put that. Initial and final. Where am I starting in this picture? I didn't actually add it, but it's in the wording. Where am I starting? I am starting at rest. What location am I starting? Z. I am located at some distance Z above it. So my initial is Z. Where is my final? Where do I end up at the end? Just before the surface, which is 0. So you can see here my bounds are kind of the opposite of what you'd expect. That's where another negative sign is going to end up kicking things out for us. Yeah.
Wait, what is the purpose, the dv and the e? I don't understand that.
So right now we're doing this integral. I'm going to move it to another slide. Just give me some more room, and then I'll point that out. We're trying to find how fast it's going to go. We're finding how fast it's going using conservation of energy. To do conservation of energy, I need the change in potential energy. Change in potential energy is defined as negative q times the integral of E dot ds. That's a dot product. Dot product is the same as the magnitude of the first vector times the magnitude of the second times cosine of the angle between them. So we need to know their directions to find the angle between them. And the angle in this case is 180. All right, so this means that my change in potential energy, if we put all the pieces in, is QE from Z to 0. Because we start at Z, we end at 0. My electric field is sigma over 2 epsilon naught. And what do you think I want to integrate over? What variable? Which way am I moving? Up, down, left, right? Down. Up, down. In this case, what do we define? What kind of variable did we happen to use for up, down? So we're going to integrate with dz. You could do y. Y is fine. I only picked z because I happen to say it was a height z above it. You could do dy if you really want. It's not going to change anything. Yeah.
Is that a 2 or a z in the top?
Oh, yeah. So that's a 2. So something else, so this is good to point out. This is a little notation thing that maybe you've seen, maybe you haven't. There's some tricks to helping. When you're doing a bunch of math, you're going to write a bunch of numbers. You're going to write 2s, you're going to write z's. When I write a 2, I write a 2. When I write a z, I put a line through it. It sounds silly, but this is very, very helpful notation. It's one of those really, really helpful things because when you're writing fast, they do get mixed up. You will mix up 2s and z's. This little strategy is one way to avoid that. Also, when I do 7s, you'll also notice I put a line through it as well. So because if you write a 7 really quickly, you can accidentally put a little tail at the end. It can look like a 2. This sounds stupid. It won't be stupid after you've made this mistake a bunch of times. After you've mixed up 2s and z's a bunch of times. It will happen to you. These little optimizations to make your writing more clear. Another thing is when you write a 0, you can put a line through it for a 0 so that you don't think it's an O. Little tiny things that you pick up as time goes on. All right, so this integral is very easy. Everything is a constant. Everything is a constant. So my integral is just z, evaluated from z to 0. Again, maybe we should have done y. It doesn't really matter. Oh, and there's something I forgot here. There's a negative 1 here. You're like, where did that come from? Cosine of 180 is negative 1. Cosine of 180 is negative 1. So, we got a negative 1 here. And we're integrating we're putting in our bounds from z to 0. We plug in our numbers. QE, I'm going to start to put them together. QE sigma over 2 epsilon naught. I'm going to let you all see this. The negatives cancel. 0 minus z is negative z. I'll write it just to be kind. Oh my gosh, my negative signs cancel. So long story short, 2 epsilon naught times z. This is my change in potential. This is my change in potential energy. We have one last step. Always keep your target in mind. Don't lose track of what you're doing. What's the whole point of this? Find the velocity. So we're just going to take this and chuck it in there, and it's going to work out great. This is QE. And then on the bottom, there's a 2. Now, we did kind of cancel out this negative sign. We could have left it here. So, if you're like, here. Let's see. Do I want to can't? So, know that the negatives all canceled. Epsilon naught times z. Yay! It's better. All right. That equals my change in kinetic energy. What's my kinetic energy initial? Yep, it's 0. It's not moving. So boom, that's gone. We're so close to being done. So Q, the charge of an electron times sigma over 2 epsilon naught times z equals 1/2 mv squared. The halves are going to cancel. And you solve for v, and it's going to be the square root of Q E sigma over epsilon naught times the mass of the electron. And there's a z up there as well. And that's the answer. All right. What's the takeaway from this problem? That was a lot of steps. Remember, I show you all, the problems I show you all in class are the more complex ones. When you go through the problem sets, it's not going to immediately kind of jump to this. This is kind of at the end of the energy stuff. What is the takeaway from this? If you're asking how fast something's moving, you're going to use conservation of energy. How do I find the change in potential? You can do an integral. That's kind of the main thing here. You do this integral, you find it, yay, you get the velocity. Yeah, 1/2 mv squared. Good old kinetic energy.
Probably a stupid question, but how is the integral a constant? Because sigma not constant.
Sigma is a constant. Sigma is a charge density. That's a constant given in the problem. Yep.
Wait, I have a question.
Yeah.
What's on the top? V equals square root.
QE, charge of the electron, times sigma, times z, divided by epsilon naught, and divided by the mass of the electron. It's just rearranging this one.
Okay, what about the one line above?
Here? That's the change in potential energy. This is just deriving it all.
Yeah, like after the negative 1, what is that?
Negative z. Negatives cancel.
Oh, negative z.
Yep. Yeah.
How did you set your kinetic energy equal 1/2 mv?
That's the definition of kinetic energy. Yep. Yeah, good question. Kinetic energy, definition of that equation is 1/2 mv squared. I think that might be on the formula sheet. Not sure.
Are we dividing by, is E both the numerator and denominator?
E? So this is a subscript. This is Q subscript E. This is M subscript E. It's a charge, not Q times E, Q subscript E. Subscripts are an adjective. So this is a translation thing. Whenever you are doing math and you write a subscript, that's an adjective. What is this the mass of? This is the mass of object 1. Yeah, good question. All right, I'll answer a couple more and then I just got to keep moving. Yeah, so question was, why do we go from ds to dz? ds is the direction I'm moving. So what direction am I moving in this problem? I'm moving in the z direction. They're the same thing. Yep. All right, one more. Want to check? Okay.
What is the kinetic energy initial product now?
It's not moving. In the beginning, no kinetic energy. Velocity initial is 0. Kinetic energy initial is 0. All right, one more and then I'll keep moving. Is E not posted, the value of it? Yeah. 8.854 times 10 to the minus 12. Yep. All right. So, moving onwards. Great. Now we actually get to talk about potential. This whole doing potential energy thing is just introducing the idea of potential energy. We're going to actually work with it in a slightly easier way. We're going to start introducing voltage. So previously, something we've been doing is we said, hey, there's a force on something. What causes that force? We divide by Q. We divide by the charge at that place, and we introduced a field. So we took the force divided by the charge in it, and we got the electric field. Now we can ask ourselves, what makes the potential energy? So why is it that when two charges, so I got one charge here on the left, one charge here on the right, why does this system have potential energy? Just like we asked, why was there a force? And we said, let's imagine that this thing makes a field everywhere, and this other charge is in that field. We're just going to change the wording now. We're going to say, what if this thing makes a voltage everywhere, the left charge, and the right one experiences that voltage? So this is kind of the new thing. Just like this, we took the force divided by Q. We are now going to take the energy of the system. We're going to divide it by the charge at that location. And that's going to give us this mystical quantity called the voltage, which is, if I multiply that voltage by the charge in that voltage, it tells me the energy of that system. So just like we could take the charge, multiply it by the electric field and get the force, I can take the charge, multiply it by the voltage and get this potential. So it's another way of framing things. And I got some nice pictures that kind of show this. Let me give you all, so there's some pictures I'll show you all, and I'm going to connect this to stuff that you understand currently. So there you go. Same thing I just wrote. Take the force divided by Q, you get the electric field. Take the energy divided by Q, you get this thing called voltage. Now, voltage is one of those things that almost everyone has heard about, and almost no one knows what it is, because they haven't learned about it. All people generally know is that I plug stuff into a wall, there's a voltage, and I get some electricity. I have a battery, it says 1.5 volts. Another battery that says 9 volts. 9 is a bigger number than 1.5. And that's kind of the most people know.
Is it true that 9-volt batteries are just made of like 40?
Yeah, 9-volt batteries, depends how they make them. Could be just a bunch of 1.5s in a row. We'll see why. All right, so here's the energy. Okay, Q1, Q2 over R. We talked about this. What is the electric potential based on that definition I just gave you? And I want to find the electric potential made by charge 2. So there's the potential energy of two charges. So there's charge 1, charge 2. What is the electric potential made by charge 2 where charge 1 is located? That's the question. Is it KQ1 over R12? R12 is just the distance between them. Is it KQ2 over R12? Is it KQ122 squared over R12? Or is it K1 over R12?
You just have to know, like, this is as we like assume that the charges are already in the battery.
What?
Like, how do you know there are two charges? Is it being like
That's how we imagine there's another charge. You guys have it. Yeah, you pretend like there's a fake charge Q1 in this potential. It's kind of like the same way we did field. We pretended like there was a positive charge there. Yeah. All right, give you all 30 more seconds. All right, 10 seconds. And 5, 4, 3, 2, 1. All right, so remember the thought process here is kind of like the one before. Charge 2 is making a potential everywhere, and then we can place charge 1 in that potential to give us an energy of the system. Just like one charge makes a field, the other experiences a force, one charge makes a potential, in this case together, they experience this energy. So, if I say what's the electric potential made by charge 2, it should probably have charge 2 in it. So it's not that one. It's not the one with charge 1 by itself. And it's definitely not the one at the bottom, because that also doesn't have charge 2 by itself. So, go back to that definition. Voltage caused by a charge is the energy of the system. That's the two charges here. Let's just call it like 1, 2. And then we're going to divide by the charge, this like fake charge that we place in it. This hypothetical charge that was in it. So, we get the voltage that charge 2 makes is K, Q1, Q2 over R12, all divided by Q1. The Q1s cancel, and we get KQ over R. This is the voltage made by one charge. Yeah. Yeah, so Q1 is the one that gets placed in the voltage. One charge makes the voltage, another charge gets placed in the voltage. Just like one charge makes a field, the other one gets placed in that field. Yep. All right. So, this is the equation for the point charge derived. Voltage, we're going to see that in a second. Is voltage the unit? This is one of those this is the only unit that we talk about where the name voltage is also the unit. The symbol and the name are the same. It's one of the only ones I know of that follows this. So here's the definition. The change of potential energy experienced by a test charge with a value of 1 coulomb. So if I put a charge of 1 coulomb, this is the amount of potential energy we'd gain if it was placed in it. We derived it before. The definition here, if you're like, what would happen here? This is the integral definition. The Q just went away. We just used the definition of potential energy with the integral. So we just used this change of potential energy, and it was that negative Q integral of E dot dr. Through the magic of dividing by Q, the Q goes away. So the voltage is the integral of the electric field. Great. So a lot of this is mathy, and then I'm going to try to teach you all the concepts without the math. And then the point charge we just derived. So that's the math part. Give you all a few moments to kind of see that, write that, whatever. And then I'm going to actually talk about an easier way to understand voltage kind of outside this math. And as I mentioned, the variable is V, and the unit is also V. Volts. So we won't actually say 3 voltage, we'll say 3 volts, but they basically sound the same. Named after a guy whose last name was Volta. Shocking, right? They're always named after someone.
What do you even have your own?
No, good luck. Never. I'm not doing any research, so I'm spared that suffering. It's good stuff, but I'll leave it for someone else. Anyway, here's what I want to connect it to you all. We know about a different type of potential energy, gravitational potential energy. We are very familiar with gravitational potential energy, fingers crossed that is true. How do I make this water bottle gain more gravitational potential energy? Yeah, you know it higher. You could change its mass, but that's a little trickier. I'd have to go get some water. Like, the easiest way is just increase its height. How do you make something have more electric potential energy? Increase the voltage difference. Voltage is like height. Voltage is like height. If you want to increase the energy in a system, take one charge and just kind of move it, in this case, like to a higher voltage. So I have a picture here at the end. I put it at the end of the PowerPoint, but I'm actually going to show it to you all now because I think it shows a nice analogy. So I'm going to actually jump way to kind of the end here to show you all this picture, and we'll revisit it in a bit. So I keep telling you it's like height, and this is a nice visual for this. Oh, before I even get to that, this is a scalar. This is a scalar. Electric potential, also another thing, aka voltage, they're the same thing. When you hear the word electric potential, it's the same thing as voltage. Same exact thing. When you hear the word voltage, it's the same thing as electric potential. Is a scalar, meaning no x and y components. There is no such thing as an x and y component when it comes to voltage. Also, you can have a negative voltage. You're like, how does that work? If I said how tall I am, all right, yeah, so here's my water bottle. If I set the ground as my reference, what is the height of my water bottle roughly in meters? Positive or negative? Positive 1 meter. If I set my reference as the ceiling, what is the height of my water bottle roughly in meters? Negative 5 meters or so. Height can be negative. So can voltage. All it means, all you care about when it comes to voltage is the difference between the two. Whenever you all solved conservation of energy problem in Physics 1, you didn't care where you set 0. You could set it anywhere as long as you kept the reference the same. When you all did this, if you are in the Physics 2 lab this last week, you all did voltage measurements. You had 2 probes. I really hope you kept your black probe on your multimeter at one spot the entire time, because that's your reference. That's your 0. If you change your reference, then it messes up everything. Voltage is always measured with respect to another spot. Just like height, whether or not you've realized it, anytime you said how high something is, you are referencing another spot. If you say how tall someone is, you're referencing the distance between the top of their head and the bottom of their feet. There's always 2 points when you talk about how high something is. You might not have made it explicit. We tend to just say the ground outside is 0. But like if I asked you how high up am I right now, there's an infinite number of correct answers. I could be 0 meters high if I use the ground here. I could be negative 5, 6, 7 meters if we use the ground outside, because it's actually above us. It could be millions of meters if I use the center of the earth. Height is relative. Voltage is relative. We're going to see that a bunch. So let me jump over this picture that I think does a good job of showing this height analogy. So we're going to learn about equipotential lines. That sounds like a fancy word, but if you just break it into its pieces, equal potential. That's all equipotential means. Equal potential. It is a line where the potential is equal everywhere on that line. So I'm going to jump back to this in a second, but just to give you all since this is simulation, you may or may not have used in your labs as well. Super handy. You can take a charge. If you pull this thing over and you hit this, I get an equal potential line. Everywhere on this green line, the voltage is the same value. That's why it's called equipotential, equal potential. So at this point here, it's 5.64. If I do a really good job of placing this thing, again, I'm not going to get it precise, but it's 5.64 there as well. Oh my gosh, what is it over here? It's also 5.64 if I get it precisely on the green line, which is like impossible. Okay? You all have seen these lines before if you've ever looked at a map of topography. So that's the connection that's going to show up here. If you've ever looked at a map that has topography on it, like mountains and things like that, they use these lines. They are not voltage, though. They are the height. Everywhere on those lines, the height is the same value. And if you look at these maps, so like you can just look up any topography map, and you're going to see this topography map. You can see I've looked it up before to find that picture. You get this picture. Every one of these lines, if you trace that line, the height is the same everywhere on that line. Also, when you look at this, the closer those lines are together, the steeper it is. The farther apart they are, the less steep it is. We can make an equipotential graph, voltage, after you all did in the lab, and it looks like the same thing. If you all are cool with height, you're going to be cool with this. And if I place a ball on this hill, which way is it going to roll? It's going to roll down the hill. Hopefully we're all cool with that, right? Why is it going to roll down that way? What's pulling it down? Gravity. What's the direction of the force? And this is maybe, so I'll kind of say this because I don't want People might give an answer that's kind of technically right. If I put a ball here, yes, gravity points down, but which way is it ultimately going to kind of go? Which way is the net force going to be? Down the hill. Ready for this? If I put a positive charge on this equipotential, it's also going to roll down the hill. It's going to experience a force down this surface. So in the lab that you all did last week, you made an equipotential circuit. You all made a graph, and you can actually see it. Positive charges will roll down that voltage. They'll go from a higher voltage to a lower voltage. Positive charges will act just like a ball rolling down a hill. Negative charges will do the exact opposite. Negative charges are going to roll up this hill. This hill representing voltage. So all that means, the force is along the change in voltage. The force is along the change in voltage. And there's a slide kind of here at the end that kind of shows that. We've been doing the integral, but if you rearrange it, if you find the derivative that tells you the direction of change, not going to worry about this too much. Again, don't worry. I'm going to come back to this later. I just want you all to be cool with that. If you're cool with height, voltage is like height. That's what I want to connect in your brain. Yeah.
So if the charge goes down the hill,
Yeah.
does it lose potential energy?
That's a great question. Yeah, as the charge goes down the hill, does it lose potential energy? Yes. What is that energy converted to? Kinetic energy. So, but what's important here, is a ball going to roll down a flat hill?
No.
If you have a voltage value that's 10 volts, and it's 10 volts everywhere, nothing's going to happen. So my connection to y'all here is when you have a battery and it says it's 1.5 volts, what that means is that one side is 1.5 higher than the other. So if I have a 1.5 volt battery, that means that this side, for example, could be 1.5 volts and the other side is 0. Or this side is 3 volts and this side is 1.5 volts. I don't care what the numbers are as long as they're different by 1.5. This is what voltage is. Anytime you all see voltage listed on any device, it means the high point is, let's just say that number, and let's just say the low point is 0, because then the difference is that number. It's a difference. A ball does not roll down a flat hill. You need to make a height difference, a potential difference. So, that's my long spiel. Let's do some math on this. Voltage is electric potential, not electric potential energy. Don't get them twisted. Don't get them mixed up. This is a classic mistake that I'm glad you mentioned. Electric potential is not electric potential energy. They're different. Electric potentials cause electric potential energy. They are not the same thing. Height is not gravitational potential energy. Height causes gravitational potential energy. Unfortunately, these ones, the words are like the same. You just check the word energy to it. All right, let's do some problems. You're going to see that voltage is great. It's so easy to work with. You don't care about the path things take. That's why in conservation of energy, it was great when you all could do conservation of energy. You didn't care about the path it took. You just care about, it's all scalars. It's so good. You'll see. So this problem we've seen now, this is the third time I've given you this picture and asked you for something different. The first time I said, find the force on the top. The second time I said, find the electric field at the top. The third time, find the voltage at the top. Find the net electric potential. Another word for voltage. Same thing. Super easy. So, voltage equals question mark. How do we find the voltage at the top? We find the voltage at the top due to charge 1, which is in the bottom left. We find the voltage at the top due to charge 2. Charge 3 is at the top. It doesn't make a voltage where it's located. We're going to see why in a second. I'll kind of point that out. And you add them all together and you're done. It's super easy. So if I want the voltage at the top, the net means total. How do I find it? I find the voltage due to charge 1 at the top and the voltage due to charge 2 at the top. I am finding the potential at the top. That very, very much matters where I'm finding the V net at. V net equals question mark. Charge 3 does not make a voltage where it's located. Why? The equation for voltage due to point charges is KQ over R. Where are you located? What's the distance from me to myself? 0. You can't divide by 0. A charge by itself does not give itself energy. You need a couple charges. So, super easy. You notice I keep saying that, but just plug in the numbers and you'll see. So if I just keep it kind of vague right now, KQ1 over R1, KQ2 over R2. These are not squared, they're subscripts. And then I just put in the values. What is the charge of Q1? Q. What's the distance from that to the point I care about? A. The same is true of the other one. And the final answer is just 2. KQ over A. Boom, done. It's so easy.
So is it 2 KQA volts?
Yep. This one's a little funky because we're working in variables. We don't often write the units because the units are kind of hidden within these variables. So yeah, when you are working purely in variables, we don't tend to write the units after it, which is kind of funky. When you plug in numbers, you do. Now, if you wanted to find the energy of this system, it's so easy. I didn't ask you to do it in this problem, but it's so easy. You all want to find the energy of the system? Just take the charge at the top and multiply by the voltage at the top. If you all want the energy of the system, find the charge, Q3, multiply the voltage at the top. And so the energy here is going to be negative 2Q times KQ over A equals negative 4KQ over A. Boom, so easy. I didn't have to bring in one charge at a time, then another charge at a time, then another charge at a time. All I had to do was find the voltage due to all these charges at some point, and then multiply that charge by that, and boom, done.
How are you able to do that?
Oh, one second, yeah.
So to find the net potential, you just have to find the energy of everything with respect to the
Yep, you just find the voltage at that point, and just multiply by that. At least, yeah, the energy stored there. Yeah, and then I'll jump up there. Yeah, thank you, Q squared. Was that the same thing? Sure.
Are they the same as the last subdivision, like the electric?
Sorry, so what's repeat? So is what the same as what?
Like I'm just confused. Like are we pretending the same equations from the last slide, or is this like?
They're different. This one lost a Q. So the electric potential energy was Q times the integral. The voltage, we get rid of that Q.
So the other one was electric potential energy.
Yes. And so this one is voltage, which is V. The last one's was U. Electric potential energy. This one's just electric potential. It's a very subtle difference that will trick people up. If I ask for the word energy, make sure you're doing energy. If I do not say the word energy, don't find the energy. It sounds silly, but you will make this mistake. I will ask for potential, electric potential, and you will accidentally solve for electric potential energy at some point if you do enough of these.
I have a question on how do you get negative 2Q?
Oh, down here?
Yeah.
If I want the energy of the system, Q3, the value of Q3 is negative 2Q.
Oh, okay.
Yep. All right, one more and then I'll keep moving. Yeah, this one.
I don't understand your explanation on like the V equals KQ over R, like how it's by itself and the R equals 0. You can't have that.
So we're finding the electric potential up here. So we're going to do KQ over R1. What's KQ over R2? We're going to find the voltage due to charge 1, then the voltage due to charge 2. Charge 3 doesn't make a voltage where it's located because the distance from itself to where it's located is 0. And so you can't divide by 0. All right, I'm going to keep moving. If we have more questions, I'll do it at the end, but I just got to keep things rolling. All right, so this one, we're going to go ahead and this is the integral one, so I'll show you this. It's fairly straightforward. Derive the equation for the electric potential at distance z above an infinite line of charge that carries a uniform charge density of lambda. Since the charge densities expand to infinity, the potential won't be 0 at infinity, so instead we're going to set the potential equal to 0 at R naught. You're like, what's this? I'm going to walk through it and you'll see. So what is this one? I got an infinite line of charge, and previously I said, what's the electric field here? Now I'm asking you, what's the voltage here? What's the voltage look like around an infinite line of charge? That's the goal. How are we going to do this? We're going to use the integral equation. Negative integral of E dot ds. Why do I have to do an integral? This is an infinite amount of point charges. I can't just do KQ over R, KQ over R, KQ over R. There's an infinite amount of them. How do you add up an infinite amount of them? An integral. Now, this one we're going to take a bit of a shortcut. We know the equation for the electric field due to an infinite line of charge. We've derived this in the past. If we go over to the problem set, that is one of the problems that we have solved a couple times now. And the reason I mention this is if I gave you a problem like this in a test, what I would do is I would say, hey, here's an electric field equation. Find the voltage at some point. I would give you the electric field equation. I wouldn't make you do both. That would be a little bit too much work, especially for a multiple choice. So we just kind of scroll on down. There it is. The infinite line of charge is K2K lambda over Z. That's the equation for the electric field due to an infinite line of charge. Where do we get that from? We've done it 2 times now with Gauss's law and with an integral. Check that out for yourself. 2K lambda over Z. So if I want to find this potential, I'm going to integrate 2K lambda over Z. Now that stays there. And we're going to integrate. We're going to set the potential equal to some distance R naught. So that's going to kind of be my beginning. And then my final position is going to be where I'm located, which is at Z. We're integrating from some place where the potential is 0 to some place where we want the potential. If you're like, why are we doing this? Why am I integrating from some place where the potential is 0 to the place I'm located? If you wanted to figure out how tall I was, where is a convenient place to set 0 at? At my feet. If I set 0 anywhere else, it's just a bit more work. It's convenient to set 0 at the bottom, and then the top will just be how tall it is. If we set 0 where we start and where we end up where we end, then that's going to tell me the voltage. All right. Now, this R naught, we got some options. I'm going to go ahead and set it out here. The reason I'm going to set it out here is a reminder to you all. I'm going to actually write this way. Remember that we are, and I'm going to move things around. V equals question mark, some distance Z. R naught is up here. Remember, y'all, this is a dot product. So, same thing. What's the direction of the electric field? Oh, it's up. What's the direction I'm moving? Oh, it's down. What happens? What's the angle between these? 180. Why is that useful? It makes the negative sign go away. They all kind of connect together. But this integral is super simple. You all can 100% do this integral. ds, what direction is my thing moving? Up, down, left, right, circle. Up, down. What are we going to integrate over then? dz. Super easy integral. 2 is a constant. K is a constant. Lambda is a constant. It's just the integral of 1 over Z. It's natural log. It's super, super simple.
The angle is 180 because it's pointing up.
Because the electric field is up and because the direction I'm moving is down. Yep. I set R naught some distance farther away. So the negatives cancel. Boom, boom, gone. So I get 2K lambda times the natural log of Z evaluated from R naught to Z. It's not ideal to have the same variables as your limits, but whatever, it's fine. And the solution to this, again, I keep running out of room. I will just copy. I mean, you can see it right here. There's my answer. If you're like, whoa, how did that? Okay, so in this case, they made R naught somewhere closer. So the bounds are kind of different here, but I'm not too worried about it. Either one of these would be fine. If you're like, whoa, what happened here? If I had set R naught at some point down here, it would have resulted in us being able to get this answer. So my answer here, and if you're like, well, what if this is on a test? Don't worry. I'll tell you what to set your initial and final to. So this one is actually going to be Z over R naught. Don't worry too much that they're flipped because this R naught was arbitrary and I didn't specify above or below or anything like that. This is some random spot, so it's just a negative sign that's flipped. You're like, how did this happen? This is this is the identity with natural log. Natural log of something minus natural log of something is natural log of them divided between each other.
How come you're able to substitute in the 2K lambda z?
Oh, that's the equation of electric field due to a line of charge. Yep, it's a good question. All right, so if I gave this to you on a test, I would say, hey, here's the electric field. Here's the direction we're moving from here to here. Find the voltage.
That negative one came in because the z is pointing downwards.
It's because the direction of motion is opposite to the direction of the electric field. Yeah, so they're 180 to each other. Yeah, it's a good question. All right, now let's see if this idea of voltage and height makes sense. Because you're not going to see a nice height map when you're doing these problems. You're going to see this is even more generous maybe than what you might get. A proton is released from this dot. At this dot, it's at 0 voltage. What will the proton do? Will it remain at the dot? Will it move upward with a steady speed? Will it move upward with an increasing speed? Will it move downward with a steady speed? Or will it move downward with an increasing speed? It starts at 0 volts. Above it is 50 volts. Below it is negative 50 volts. Why? Other charges exist and are making this happen. Don't worry about why. Just know that those voltages are what they are. There's generally some charges or something that would be causing that. We'll actually chat about that. We'll make up ideas. What's the answer? All right, 30 seconds. All right, in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So, how do you answer this? Again, I keep pressing this because voltage is one of those things that a lot of people don't understand about. You know about height, so just connect this to height. Pretend that I released a ball at some point, and there is some place above it that's 50 meters higher, and there's some place below it that's 50 meters lower. What is that ball going to do? That ball is going to roll down to the lower height. And not only is it going to roll, it's going to roll faster and faster and faster and faster, because you start at rest. Literally think of what happens when you let it go. It speeds up. It's going to keep speeding up. To start moving at all, it must start speeding up, and it will keep speeding up. So think of something sliding down a frictionless hill. So the answer here is it's going to move downwards with an increasing speed.
So you're saying when a proton's released, it always like moves down?
I'm saying if there's a higher voltage above it and a lower voltage below it, it will go to the lower voltage. Only because there's a difference in voltage. If this problem was 0 volts here and 0 volts here, nothing would happen. If this problem was 0 volts everywhere, that's flat ground. Nothing happens. All right. What if it's an electron? Same problem, but it's an electron now. Electron is placed at 0 volts. Which way will it move? Will it move? Stay at the dot, upwards with an increasing, with a steady velocity, upwards with an increasing, downwards with steady, downwards with increasing. All right, 20 more seconds. All right, in 5, 4, 3, 2, 1. So, if we had a negative mass would move which way? Uphills or downhills? It would move uphill. Why? Because F equals ma. If mass is negative, it makes the force opposite the direction that it's going to make a negative acceleration. So, we don't have negative mass, but we do have negative charges. Negative charges are going to go the opposite direction. They're going to move upwards with an increasing speed. And now I'm going to explain this to you 2 other ways. Let's explain it in terms of energy. Remember, y'all, that energy is Q times V. That's the equation for the energy of a system. The charge that's there times the voltage that it's in. So, what's the energy when it's at 0 volts? 0. Now, I am also going to do something important here. Electrons, are they positive or negative? So let's chuck in negative. So I'm going to write U equals Q times V. So in this case, it's going to be negative Q times 0, which is 0 joules. That's how much energy it starts with. Remember, a rule of the universe is everything wants to go to lower energy. Everything wants to go to lower energy. So let's look at the energy at the top here then. What's my energy at the top here? It's negative Q times positive 50. That's negative 50 Q. It's a negative number. What's my energy here at the bottom? It's negative Q times negative 50. It is positive 50 Q joules. So it's going to move up to lower energy. A negative number is smaller than 0. A negative number is smaller than 0. So that's why electrons go up. When you work with a proton, everything's positive, so a lower voltage is a smaller value. All right, another way to explain this is how do I even make this voltage? How do I even make a positive 50 on the top? How do I even make a negative 50 at the bottom? Remember, for a point charge, it's KQ over R. So what sign of charge will make a positive voltage? Positive charge or negative charge? If I put a bunch of positive charges up here, guess which way negative charges going to want to move? Up. How do I make a negative voltage? Put a bunch of negatives down here. Which way is a negative charge going to want to move? Away from the negatives. It all connects together. This is another way of explaining the stuff I've already taught you, but voltage is so nice. If you remember conservation of energy, you can solve problems with conservation of energy that you couldn't solve with forces. Remember the ball, if you had like something sliding down a hill that had a crazy path, you didn't care about the crazy path. What's the example that we're going to see? If you have a battery hooked up to a circuit with a crazy path, we can use voltage to figure out what's going to happen. We don't care about the path of the wire. We don't care about how wiggly it is, how long it is. We just care that this side is 1.5 volts and this side is 0 volts. We just care about the end and the beginning height. So that's a foreshadowing of circuits. Now, the wire needs to touch both ends, otherwise you don't see the difference. If my wire is disconnected, so this explains why, if you all have a wire and it's disconnected from both ends, this entire wire is 1.5 volts, i.e. it's flat ground. It does not become an incline until you connect it to the bottom part.
Probably a weird question, but what's the deal with the positive negative terminal?
So we'll chat about that more. Positive is a high voltage, negative is low voltage. That's the quick answer. When you all have a battery, positive terminal is a high voltage, negative is a low. Subtract the 2, and that's why you use a multimeter. All right. I still got a couple more things. So this is just a nice summary slide of everything I said. Electric potential is Q times delta V. Electric potential is always a difference. Other things, positive charges, yada, yada. All right. Let's see if this one, I'll do one more question, then we'll call this good. And then we'll chat about equipotential. This one prepares us for next class, because next class we're going to talk about capacitors. So let's see if y'all can get this one in our last 3 minutes. A positive charge is fired through a small hole in a positive plate capacitor. Will Q speed up, slow down once inside the capacitor? Will it speed up, slow down, or neither speed up nor slow down? Yeah, once it's inside. So the question is, once it's here, what's it going to do? Yes. Once it's inside. This is a capacitor. We're going to see that next class. Between the plates. Yeah. It is right here. Yeah. All right, we'll close this out in 5, 4, 3, 2, 1. All right, y'all could have answered this without knowing anything about voltage. It will speed up. But my next question, next class, why will it speed up? It gets repelled by the positive, attracted to the negative, forces, all that good stuff. The question next class is, what is the equipotential going to look like inside of it? What's the height map going to look like inside of a capacitor? Again, height in air quotes. It's voltage. We'll do that next class.